Hi everybody, I'm Kate Prebble, so I'm an investor at ICM Limited. We invest in companies including quantum computing startups. And it's my pleasure to moderate this panel today of new faces. So starting from the far left there, we have Oded Melamed from Quantum Source, Vinet from Quobly, and Stubbemann from aqora. So to start off, I might just hand it back over to there and for you to do a quick introduction each about yourself and your business, and then we'll run into questions and discussion.
Okay, so my name is Oded Melamed. I'm the CEO and co-founder of Quantum Source. We are photonic-based quantum computing company. I've been working for the semiconductor industry for almost 30 years. My previous company was Altair Semiconductor. We developed IoT solutions for various applications. The company was acquired 2016. I spent 4 years in the Japanese corporate which acquired us, Sony, and I thought that this is the end of my life and I should go to retirement until I met a guy which is sitting here, Professor Barak Dayan, and we decided to establish a Quantum Source. So maybe after the introduction by the other guys, I can tell about Quantum Source.
That's good.
My name is Vinet. I'm CEO and co-founder of Quobly, and I don't beat you. I've spent 20 years in the semiconductor industry, but before that, I made a PhD in quantum physics, and actually, my accountability in the semiconductor industry was to do development and technology for the semiconductor industry, pushing the performance of the transistors by decreasing their size. And what happened is that everything that we were fabricating was provided to the labs I made my PhD with, and for 15 more years, they've cooled down samples from the semiconductor industry. So in 2016, we were the first team in the world to demonstrate that we can actually fabricate a qubit thanks to a industrial CMOS technology. And based on that, we incorporated Quobly end of 2022. So today, Quobly is actually building quantum computers based on silicon, based on the semiconductor industry. And I threw away my cell phones, but each of you, you've got 50 billions of transistors in your pocket. We're turning the transistor into qubits.
Fantastic. Yes.
Yeah, and I'm Jannis. The correct pronunciation is Jannis Stubbemann, the German way. I haven't spent any time in semiconductor industry. My background is in computer science, and now I'm the co-founder and CEO of aqora. We are building the online competitions platform to bring together enterprises with use cases, quantum experts with solutions for these use cases, and also the hardware providers to have one place to explore quantum computing and make it useful.
Fantastic. All right, I mean, so you can hear already that although this is a new faces panel, these are some faces that have been around the industry for a long time. But the reason why it's the new faces panel is that all of these companies are relative newcomers to the industry. So that's where I'd like to start off the discussion. Is we've been hearing a lot of conversation about the second wave of quantum computing, and yeah, maybe Maud, you can start with why it is that there is this second wave. What are the challenges that we have seen in the first wave of quantum computing that your companies are now answering?
Okay. Well, I do believe that to be completely useful, quantum computing needs to go for the millions of qubits. And we're at the stage where there are prototypes and they are already providing value to the industry, and we've got lots of wonderful examples throughout the day. But if we actually want to deliver the full value of quantum computing, we need these large-scale quantum computers that are the ones that are supposed to revolutionize the computation. And that's what we're aiming at, and that the whole rationale behind using the semiconductor industry and especially turning transistors into qubits is because we are leveraging an industry that scales. We have roadmaps to millions of qubits. What it costs us is that right from the start, as we are going for the long term, we need to think in terms of system, and we do a full stack optimization in order to take the full potential of the technology that we are leveraging. So we think the control at the same thing as we think the qubit architecture. We think of the software at the same thing of our physical architecture, because that's so intertwined that this is what we need to optimize. So to answer your question, where the company were providing roadmaps, at least viable roadmaps, because we're leveraging existing scalable technology to go to large-scale quantum computing.
So if I may add,
Yeah.
and that will also provide some insights to our motivation to establish quantum source. I'm even more deterministic. I think that unless we will have large-scale fault-tolerant quantum computers, we will not be able to realize the potential of quantum computation. And the reason we need millions of qubits is because of error correction. If we want to execute algorithms with billions of steps, and this is really what is needed in order to execute algorithms which has some commercial viability or commercial usefulness, we need the logical qubit error rate to be very low. We need it to be like 10 to minus 15, 10 to minus 16, and even lower. And that means that each and every logical qubit need to be encoded by thousands of physical qubits. But if we look at what is presented today or what is available today, we see quantum computers with maybe 1,000 qubits, physical qubits, or even less. It's a very nice scientific demonstration, but the use case is limited. There is no commercial value in such a machine in my mind. Mm-hmm. If we look at the technologies out there, photonic was probably one of the first technology that developed from ground up to support large-scale fault tolerance, and probably silicon as well. And it does so by combining small clusters of entangled photons to construct a larger system. And many people believe that this is the route to achieve large-scale fault-tolerant computation. The issue with photonics, however, is that constructing those small clusters of entangled photons is very, very tough. Even creating a cluster of 10 or 20 entangled photons. The processes that exist today uses probabilistic processes with a very low probability of success, and that creates a system which is super complex, super big, and very expensive. In quantum source, we address this specific issue. We develop a technology, a proprietary technology based on a cavity QAD. It was developed in Weizmann Institute of Science in Israel. And leveraging this technology, we can construct small clusters of entangled photons in a deterministic way. And more specifically, we trapped single atoms on a photonic chip that we manufacture in standard fab to both generate single photons and to create the entanglement between the photons. By doing so, we can improve by many orders of magnitude this very complex process. So that was our motivation. We were established in the year of 2021. We raised $27 million from Israeli VCs and US VCs, including Dell Technology Capital, which is their first and only investment in the quantum space. I do believe this is the largest seed round in the quantum computation hardware. We have 42 employees. About half of the employees have a PhD in physics or electrical engineering. So that's about us. So just to summarize our motivation. So we think that large-scale fault-tolerant computation is a must, and this is the target that should be for all the industry. We are betting on the photonic route. You are betting on the silicon route. And within the photonic route, we found the solution which is orders of magnitude better than what other people are developing. So that's our motivation.
It's interesting. Before we move to the software and application side of things, it's interesting, this connection between the semiconductor industry. Just quickly, do you both think that that's a theme of the second wave, utilizing these existing manufacturing facilities?
Well, actually, building billions of identical objects costs a lot, and to do so, and it needs reliability, it needs yield, and currently there's an industry who can do that and does it pretty well, which is the semiconductor industry. But to do that, the semiconductor industry didn't wait for quantum computing. There is a huge consumer market, and there are millions of billions at stake, which are enabled the semiconductor industry to be at the angstrom control and to reach what they can do now. So us as a quantum industry, we've got to be smart and to reuse in a very smart way what has been developed. And if we can just leverage what has been developed for the mainstream semiconductor industry to build quantum computers, we actually have a path. And what we did in Quobly, when I said that we were the first team in the world turning a qubit, turning a transistor into a qubit, it's because it's not obvious. It's not that obvious. Transistors, they do deliver a lot of current at room temperature. Whether in silicon spin qubit, we manipulate the spin degree of freedom of a single charge at low temperature. We are in the same material, still the optimization is different. But from all the data that we've gathered, now we've found a path, and we demonstrated that it is possible. We found a path to turn those transistors into a qubit. And this, when we leverage this, we'll leverage the yield, the reproducibility, and the performance ingredient of the semiconductor industry. And that's not only about qubits. I was talking about system. Building billions of qubits or millions, we can just discuss. But it takes a lot of control electronics to implement the algorithms that we're going to do on these qubit arrays. And this demands some circuits to control that. And by reusing the semiconductor industry, we can actually do system on chip, where we've got the control electronics together with the quantum chip array, and we do optimize the quantum correction, the quantum error correction, because we reduce the latency, we reduce all the parasitics, and we have a way to optimize and arrange our arrays in such a way that we can leverage a lot of know-how that has been generated in the past.
Interesting. Right. And Yannis, could you talk a bit more about how this looks from an applications perspective?
Yeah, right. Yes.
What's missing?
Yeah, yeah. So we are not coming from the hardware side, but rather from the application side, and we see it very valuable to start exploring the different applications and the different use cases, and start to understand which one actually will have this advantage at some point. It could be in the million qubit area, but we could see that the moment we have hardware with the number of qubits that you cannot simulate classically anymore, it's likely also about the fit of the right use case to run on this hardware that can then prove valuable and make the quantum computing useful, at least on a small scale for the first time.
Right, and you're thinking of how to do this for all sorts of underlying qubit technologies?
Yeah, right, exactly. I think that the very first quantum advantage will likely be the right fit of hardware, algorithm, and use case.
Interesting. All right, and I mean, so we can kind of see this from two angles, right? There's this hardware side that's emerging that has spotted the potential limitations of scale of existing quantum computers and a real focus on, okay, how do we get these numbers up as high as possible? And at the same time, we have from the other end, how do we bring forward end users to actually skill up so that they can eventually use these quantum computers? And that kind of brings me on to this next question as comparative newcomers, at least with the launchings of your companies. What is it that you've like? What are the advantages of being a newcomer? And yeah, also what are the disadvantages? And perhaps we'll go back to Oded.
In quantum computing, I think that there is a huge advantage of being a part of the second wave. We learned a lot from the first companies that introduced the quantum computers to the world. We understand the limitations. We understand that what is possible and what's not. And if you would ask people maybe 6 or 7 years ago, how many qubits you would need in order to run something useful, they would tell you, wow, 100 qubit system will do the work. Right now we know that this is not the case. So there is big advantage of being at the second wave, learning the lessons that the current players have. So that's one thing. Second thing, still there is no real market, let's face it. So in standard markets, the first comers are those that are probably going to be the winners because they capture the customers, they capture the market, and the late comers have very difficult time. In our case, there is no market. It's a market of scientists and companies that would like to explore and play with quantum computing, but there is no market. So whoever will be able to reach to the end goal, which is fault-tolerant, large-scale quantum computer, will win it all.
Right, so that's the real first mover advantage is at fault tolerance.
Exactly.
Interesting. And what do you think about
No,
this?
but just, well, totally agree with you. And I would say that as a second wave quantum computing company, there's one thing that we benefit from is that there was an ecosystem that was created. And though the ecosystem is still lacking from huge users, which is good for us, but now we've got companies who are looking at quantum error correction. We've got companies which are looking at calibration. We have companies who have started using artificial intelligence to provide some kind of optimization of the systems. There are many pieces of the puzzles that are looked at, which allows us to know that we can rely on an ecosystem to start looking at merging and build strong full stack companies. We don't need to detail what is quantum computing. Everybody's educated, so we can focus on the differentiating and our unique selling points when we go for investors, for instance. And that saves quite some time.
You don't have to go through this is what a qubit is, and this is what we imagine the world might look like if all this happens. And what about you?
Yeah, right. I think like right now we're in this interesting stage where there is a good outlook, a positive outlook on the quantum computing industry, well motivated by past achievements, and yeah, it's really about time to explore now different business models and applications. Like actually what we are doing is kind of motivated from the machine learning community Kaggle that was successful like 10 years ago. So it will probably not translate one-to-one, and it's not too easy to assess where we will be then in the quantum in a few years from now. But I think we're in the stage where it's very interesting to start exploring all these different perspectives on it, leaving the labs and scaling up some systems.
Right, and I suppose this is another advantage of people being educated, is you get people from different areas like
Right.
DevOps or ML and AI who say, oh, well, I understand both of these things. What can we do together moving forward?
Right.
And you ask for disadvantages.
Yeah.
I would
If there's any.
I would comment on the fact that this is nice. I said that we belong to an ecosystem, which makes it easier, but it's also a threat because as an ecosystem, we belong to an ecosystem and we need our ecosystem to succeed. And as Oded was saying, there are companies currently selling machines, and we need our ecosystem to deliver some, at least not all the promises, but to deliver some promises. Time for us to take off, because it takes time to both in photons and in silicon spin qubit. Takes time to set an industry and make it viable to the millions of qubits. So that's, we are just looking for the appropriate milestone to show that we will deliver and make sure that there is this transition between phase 1 and phase 2 of quantum computing.
Yeah, and I suppose from an investor perspective, we look at so many companies now. I mean, there are over 100 quantum hardware companies that are all telling us different things. So I suppose there's this element of just distraction, right? Like there's more noise, and you have to stand out, I suppose. And so I wanted to talk a little bit more about, well, for you to talk a little bit more about why it is that you are comparatively late starters. What is it that meant that you're starting your companies now, or in the past couple of years? Why now? Why not 10 years ago?
So maybe I can talk for Quantum Source. So we decided to establish the company after understanding what photonic quantum computation can deliver and what the bottlenecks are. And we were aware of that only, I would say, 3 or 4 years ago.
Right.
Before then, talking about photonic quantum computation was something which is very abstract. So only then we realized the potential and the challenges. And once we found the solution to the challenges, we decided to go.
Right, very clear.
So that's the advantage of second wave. Understand the challenges, find the solution, and go.
Interesting. And Mo?
I would say that, as I said earlier, we demonstrated the first silicon spin qubits in industrial technology in 2016. And kind of like Oded, and I'd say silicon spin qubit faces one challenge: to be good and deliver a long coherence time, we need silicon 28. And which provides a noiseless environment for the spins to behave like as if they were in vacuum. There was no supply chain for silicon 28 at that stage. So before launching a company, we took advantage of the fact that we were coming from the nuclear industry. And my institution is called CEA, for Atomic Energy Agency. And we took us time to go to the nuclear players and make sure that our critical element, our critical component would be available. So before we incorporated the company, we just my point is we built an ecosystem, and we consolidated also the research ecosystem, because though now we understand most of the technological challenge, there are still some scientific questions, and we gathered all the French ecosystem working on silicon spin qubits, so in Quobly currently, and it translates in the fact that currently there are 30 researchers on top of the Quobly employee on the payroll working for Quobly, and we've got this resilient supply chain that is available to support the company. So that's basically time it took us to build the ecosystem.
Right. So you identified back then that you would need all these things, and yeah, been building towards that.
Yeah.
It's fascinating.
Yeah, for us, it's actually we have a history in running in-person hackathons, in-person quantum hackathons, and we saw the global demand for it. So leaving Europe, leaving Paris, or France, and leaving Europe, and we're also optimistic on the other side that quantum advantage can happen within this decade. So we see this as an opportunity to build this platform where it can be explored on the different use cases.
Right, okay. It's fascinating. And I do want to make sure that we have time for questions. So maybe if everybody wants to just one more time, maybe we can start from this direction this time, give a 30-minute summary of, yeah, what you're trying to do as a company, and then I'll hand over to the audience to ask some questions.
We're doing the,
you know,
okay.
Yeah.
So sorry. Yeah, with aqora, we are building the online competitions platform to bring together use cases, quantum experts, and hardware providers to explore, well, quantum solutions and understand how quantum computing can be made useful.
Great.
In Quobly, we're building a hardware, we're building quantum computer based on silicon spin qubits. The rationale behind is basically we're leveraging the semiconductor industry to build billions of qubits.
In Quantum Source, we built photonic quantum computer based on a technology that enables us to generate the qubits as well as to create the entanglement in a deterministic way versus the a probabilistic way that other technologies can offer. That makes our system more scalable, easier to control, and also works in room temperature, which is another huge advantage compared to others.
Yeah. Right. Thank you very much. And questions, please.
Thank you. My name is Leonardo from Entropica Labs. My question is a bit more maybe for the hardware people, but I guess it will trickle to software. First wave of players in the hardware side of things, I have the feeling they wanted to build everything. So a lot of software was handed out from them, like from Qiskit to Cirq to Quil and so on and so forth. What do you think this second wave will do? Will it leverage the existing part? Or actually, let me rephrase it. Will you build a lot of the software that will run on your machines? Or do you think that there will be space for other startups, companies to contribute to that? Will you keep everything in-house or try to seek for help?
So maybe I can answer.
Go ahead.
At least I can answer for us. We don't plan to develop all the software stack. Like you are running your algorithm on a supercomputer, and you don't expect the supercomputer guys to write the algorithm for you, or to run the to write the operating system for you. So this is not our mission. We intend to provide very easy and clear interfaces to guys that will develop the software above it. But I know that different companies have different strategy. At least that's our intention.
On our side, we don't see the point of redeveloping all the software neither. We believe, though, that there's a strong interaction between hardware and software all the way up to quantum error correction. Because the way you perform the quantum correction does have an impact on your hardware on your hardware architecture and vice versa. So what we're currently doing is that we're building in-house expertise on those topics, going all the way up from compilation and transpilation. But we're also looking at what's happening in software, in software startups that are focused on one layer of the software stack. We do believe that they can't be very efficient without hardware companies. So we're looking for collaborations or eventually merge, fusion, you call it the way you want, to benefit from their expertise at one point. But we're at the stage where we've got our own experts in-house because we need to know what's at stake.
I have a spicy question. We have different hardware platforms? Will it be a winner takes all in the space? So if spin and silicon works, photonics is gone. And on the software side, do you see people focusing on hardware agnostic software to prevent problems with that, or will there be a branch of software that would be useless because it's focused on a different platform?
Yeah. I guess in this phase, what we see is that we start to explore more and more technologies. I assume at some point there will some consolidation happen. I don't know, like how much and how for how many players there will be this space. But for now, I guess like what we see is that it will be really this very specific match, that specific hardware will be good for specific use cases, for specific solutions. And I think that all these many different hardware providers also don't have the expertise to build all these software stacks and so on. So I think it's important to really link them as close as possible and make it possible to run like the good fits on their hardware, that there's not too much necessary to build around.
So regarding your spicy question, it's very hard to predict, but I can tell you what I think. I think that the first technology that will provide a really large-scale fault-tolerant quantum computation will win most of the market, and the other technologies that are out there and are aiming for the same target will need to show dramatic improvement, either in scale or cost or performance compared to the first comers to the target. Otherwise, they will die. So that's my take, or my what I anticipate.
I have two questions. The first one is, do you see a niche market for smaller quantum computers? And the second one is, where are you in terms of number of qubits, in terms of number of gates you can apply to a qubit?
Of course, there are niche markets, but that's not what we're talking about. Currently, the quantum computing is claiming to create thousands of billions of dollars for the whole industry. And that's not niche market that will create this value. So that's all the rationale of having this second wave of companies. That's to address the full quantum value. So yes, niche, but niche does not necessarily justify that we have so many enthusiasm around quantum computing. That's on one hand. Now, how many qubits? And that was your question. How many qubits? How many gates? or reliability and so on and so forth, fidelity. Okay, so currently currently we've got 2 qubit gates and single qubit gates, and what happens is that what we're doing is that we are looking at all the technological parameters that allows us to go from one scientific first to a industrial always true. So we're being very systematic about all the technological parameters, so that we build the devices that will provide the yield, the sufficient yield at large scale. So that's the reason why at the beginning it takes a while. This is not only about designing a few qubits, and doing 10 qubits is not easy, but you can do it in semiconductor. It's doing the billions of qubits that will be interesting, because you deal with variability, you deal with yield and reproducibility, and this is all the systematic work that is currently being done, so that we leverage the actual promise and the potential of the semiconductor industry. That takes time to set up a technology, but once it's there, you actually go for large numbers of qubits. And that's what is being set up currently in the semiconductor field.